Good morning, everybody. Welcome to good morning to you, Ruben. Good morning, everybody. Welcome to another sunny and fun morning of Chem 1105 with your host, me, Dr. White. Couple of public service announcements. One, yesterday at Walgreens, I go to Walgreens for this, I got my flu shot. Hopefully, you all get your flu shot during the pandemic. You don't want to get the flu. I'll bet. Luckily, I haven't, and hopefully you won't. So don't forget, get your flu shot. Also, if you haven't been vaccinated for COVID-19, get those. Uh, I believe there's been a email sent out from COD that if you go on campus, you're required to have your vaccinations. We're not on campus this class. However, get your vaccinations. All right, another thing. As I mentioned the other day, there were some things I had to modify in the syllabus, and I did. So let's take a look at that. If you go to Blackboard, you'll see now two new files. Chem 1105 course, student course syllabus fall 2021. K White, that's me, modified. Let's look at it. All right, thumbs up, people. Do you all see the syllabus? Who's my fast thumbs up, people? Thank you, Elena and Mackenzie and everybody else. All right, here's what I modified. Not all this, not all this, this. Now, test number 2, I moved back a week. The reason I wasn't sure is because not this Tuesday, but I believe the 12th of October, 2 days before, 3 days before that test, all of COD will have what's called in-service day. And that day, that Tuesday, there's no class or lab. So I figured, well, make it to 20, not that Friday, the 15th, but the following Friday. But if we look at where we are, we're essentially done with all the material other than going through the problem set for chapter 5, part 1. We're done. So I moved it back. Now that I realize I can't keep on schedule. That's the first change. The next change I made was in the course outline. I moved the test to the date. Remember, this column is week of, meaning this is Monday date. Test 5 will do that, and the day before we'll have the review. And I see, I forgot to eliminate that. Well, anyways, I'll have to modify it again. But anyways, and I've moved this back a little, changed things a little, and that's where we are. And actually, I could have put chapter 5 after chapter 4 here, but I'm not going to make that. Other than that, also, looks like I'm going to have to make another modification. That's what happens when you hurt yourself. I have the correct date, or will by tonight on here. Earlier, I had the correct date for the final. And those are the modifications. Any questions on the modifications? Essentially, all I've done is fixed up, and still have to fix up errors in the tentative schedule, lecture schedule, and then I changed that one test date. We're doing good. All right, no questions. So let me close out of, do two things. Close that. Didn't need that today. All right, another public service announcement. On Friday, this Friday, I will go through Chapter 5, practice problems for balanced equations. Next Tuesday, I'll go through Chapter 5, Part 1, other problems, the kind we've been doing. And the reason I'm doing overkill, and if you notice, I do overkill at times, meaning I practice a lot with you, is these are the areas students have problems with test 2. And not to scare you, but I will. Usually test 2 is the lowest average, but not always. I've had classes where it's been quite high. And that's because I've been doing overkill. And hopefully you've been doing practice. All right, now let's do the following. And right now you'd be watching me like you are if we were face to face right on the whiteboard. All right, let's take a look at this problem. 10 points. How many grams of hydrogen, H2 hydrogen gas, are needed to react with an excess of nitrogen gas, N2, to make 1.74 times 10 to the third grams of ammonia, NH3? So what are we being asked to find? What are we given? We're going to do a winky dink today, and we're going to do this stepwise. You are. First of all, right here, help me out. Do a winky dink. What are we, write down there on your paper or in your head, what are we being asked to find and what are we given? Go. All right, I'll give you another 18.7 seconds. Eighteen 18.5, 18.7, 18.75, time's up. What are we being asked to find? How many grams of hydrogen? What are we given? Well, we're given an excess of nitrogen, which means you ignore it. Whenever there's an excess of one chemical reacting, you ignore it. But we're trying to make 1.74 times 10 to the third grams of ammonia. There's no way you can go from grams of ammonia to grams of hydrogen in one step. You can't. So what do we do? Well, first of all, I remember I didn't open it up, so I better open it up. We look at important information, test number 2. This you'll be given. And we have right here mass calculations for reactions. and mass means grams, weight. And there are 3 steps. First step, convert mass of A, whatever you're given, to moles of A. Next step, convert moles of A to moles of B. And the final 3rd step, convert moles of B to mass of B. And we're going to do a winky dink. I think I talked to you about how that cartoon program when I was a little kid, you put the piece of plastic on the television set tube. That's back when we had real tubes, not now. And they'd say, Winky, help Winky Dink out, kids. Draw a ladder so he can get out of the hold of the ship he's trapped in. And you'd have to. So, step 1. We want to do mass of A to moles of A. And what is A? Whatever you're given a number of. Hint. Now, I'm going to help you out. The atomic weight, and you can look on the periodic table. You should practice this for nitrogen. The 3 significant figures is 14.0. For hydrogen, is 1.01. Now, one last thing I'll help you out with. If you go to important information, test number 2, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. And now, we're only going to ask you to try and set up step number 1. Only step number 1 now. A is ammonia. Oh, I gave it away. And don't forget, you're setting up step number 1. Quick hint. If you don't have a calculator, just set it up. All right, I think everybody's done with step 1. Let's go and do it. This is what we have. It's the only thing we have. And what do we want to get to? Moles of A. What's A? Ammonia. And how do we proceed? Well, it's time to use your good buddy, your good friend, unit analysis. All right, let's do it. I love that whistle. Whatever you're trying to get to goes on top of the ratio units. Whatever units you don't want to get rid of, goes underneath. And now I'll write those in. And where do I get the relationship between moles of ammonia and grams of ammonia? We have right here, 1 mole of a compound equals the molecular weight of that compound in grams. Well, I need the molecular weight of ammonia, and that's the molecular weight of a compound. In this case, ammonia is the sum of all atomic weights of that compound. So I need the molecular weight of ammonia. And there's 3 hydrogen and 1 nitrogen. And the atomic weight of hydrogen to 3 significant figures is 1.01. For nitrogen, 14.0. Do the math. Add these up. And remember, when you're adding, you have the same number of significant figures to the right of the decimal as the number you're adding that has the fewest significant figures to the right of the decimal. In this case, this has 2 significant figures. Anything after a decimal is significant. This has 1, which is the lower number. Hopefully all picked 1. And now I have to round this off. Keep the 0, use the 3 to round off. It's 4 or less, so I'm going to drop it. And therefore, 17.0 is the molecular weight of ammonia. And for every 1 mole of ammonia, you have 17.0 grams of ammonia, NH3. And now if I look at this, grams of ammonia divided by grams of ammonia, and anything divided by itself equals 1, cancels out. This cancels out, and I'm left with moles of ammonia. Now, something I didn't do yesterday that I'm going to do now, and let me open a spreadsheet so I can. Bear with me, I have to open it up and get it. All right, so we want 1.74 times 10 to the third divided by 17.0. So I'm going to go to my spreadsheet. And I take all right, let me do a real quick thumbs up, people. Do you see the spreadsheet on your screen now? Thank you. All right, let's take a look at this. This is what my calculator gave me. If you go back and look at this, you're multiplying, dividing exact number, 3 significant figures, 3 significant figures. Now, the reason I'm doing this right now is to show you there are 2 ways you can calculate a multi-step problem like this. And what I mean by calculate is rounding off. One is round off at the end, the other round off at each step. And sometimes those numbers are different. So if I round this off to 3 significant figures, it would be 1.02. Now, the way I have it formatted, you're going to see a bunch of zeros after 2, ignore that. And it'd be 1.02 times 10 to the second. Column A will be round off at the end, column B, and it might go into column C. So we have 1.02 times 10 squared (10 square moles of ammonia. Are we done? No, we're trying to get to grams of hydrogen. So what do we have to do? Now we have to do step number 2, moles of A to moles of B. Step 2. Well, we just figured out A is ammonia, and we just figured this out. And we want to get to moles of B. What's B? Well, what we're eventually trying to get to is hydrogen. So in this case, I'm going to help you out. Moles of hydrogen. And now you've got to figure out what goes here and what numbers. And let me remind you, and I'll rewrite this. Here's a balanced chemical equation that you need. And I'll rewrite it down here. And remember, the coefficients of a balanced chemical equation give you molar relationships. And it's your turn. Everybody, help do a swinky dink time. Help Dr. White out. What goes on top and bottom of this ratio? Your turn. Anybody knows any good links to game show music, let me know so I can play it, because truthfully, you don't want to hear me humming or singing. When I hum and sing, I put on my heavy headphones so I don't hear myself sing. That's not that bad, but it's not that good, trust me. I'm a chemist. Again, you don't have to do the math. If you don't have a calculator, just set it up. All right, I think everybody's done. So how do we proceed? We use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of this ratio. Whatever we're trying to get rid of goes underneath. And where do I get these numbers? From the balanced chemical equation. The coefficient tells me molar relationships. And for this one, the 3 in front of H2 hydrogen tells me 3 moles of hydrogen gas make how many moles of ammonia? 2 moles. Again, the coefficients of a balanced chemical equation give you molar relationships. For every 3 moles of hydrogen, I make 2 moles of ammonia. And that's what I have here. And now I can go ahead and check. Notice moles of ammonia divided by moles of ammonia cancel out. And I'm left with this, moles of hydrogen. And now I can go to my, this case, spreadsheet. And to 3 significant figures, I get 1.53 times 10 squared moles of ammonia. Let me check that again. And that's what I get. Now, notice column A and B, they're slightly different. And they may be different in the final answer. Don't know. And that's why we're doing 2 now. Are we done? No. We're trying to get to grams of hydrogen. We have moles of hydrogen now. And it's time for step number 3. And that's moles of B to grams of B. And we know the moles. And once again, everybody, it's a winky-dink time. Help Dr. White out. Figure out what goes here and what goes on top and bottom of the ratio. But before you do that, it's time to look at important information, test number 2. Remember, in the past, I used to make students memorize all this. And a couple of years ago, I decided, am I testing your knowledge of chemistry, or am I testing your memory and your knowledge of chemistry? And I decided I just wanted to test your knowledge of chemistry. So for step 3, which if you notice down here, I have convert moles of B to mass of B. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights in grams. And if you notice up here, well, you can't see it, so I'll rewrite it. And it's your turn. do step number 3. Please help Dr. White out. All right, I think everybody's done, so let's get to work. We're trying to go from moles of B, in this case, B is hydrogen, to grams of B, again, hydrogen. So I put grams of hydrogen. Why? Because if we look way up here, let me clean this up. This is what we're trying to eventually get to. So in step 3, it's time to use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. Now, I'll write that in. I'll have grams of hydrogen and moles of hydrogen underneath. And let me just show you something I've sort of implied, but if you just multiply the units, this times this, divided by this, you'll see this over this cancel out because this divided by this, A divided by itself equals 1. Now, here's where unit analysis helps you out. Well, first, let's put in the numbers, then I'll show you how to tell when you make a mistake in a step like this, which is a good thing. All right, where do we get these numbers? Where do we get a relationship of moles of a compound to grams of a compound? Go to test important information, test number 2, and the molecular mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights of that compound. So what we need here is for every 1 mole of hydrogen gas, H2, this is the molecular weight. So the molecular weight of hydrogen gas, what's that? The sum of all atoms, 2 hydrogen. The atomic weight is 1.01. Multiply this. This is an exact number. This is 3 significant figures. And that's 2.02. So we put in here 2.02. And now we're ready to go. So let's go to our spreadsheet. Now, at this point, these two numbers, now I'm going to get fancy. Let's hold on. Let me make sure. Yep, you can see the spreadsheet. These two numbers in the yellow box are my calculations, what your calculator has to. But now we have to round them off to 3 significant figures. And if we look at A3, that rounds off to 3.110, and E is 10 to the power 2. Now ignore all the zeros. So that would be 3.10. Now, if we look at B3, this one, that also we'd round off to 3 significant figures. And here we get 3.09 times 10 squared. Forget about the zeros. And notice they're different. And which is correct? On my test, both will. On problems like this, which are multi-step, I calculate rounding off at each step, column B, or rounding off at the end, column A. So the correct answer for this is either and that's the final answer, either one of these, depending how you round off. Now, I'm a round off at each step guy. I've been doing that for many decades. I know chemists who do it at the end. And this slight difference really doesn't make a difference in a final plant procedure, which I'm going to talk about. Now, one thing I do want to point out, a benefit, I mean, really a benefit of unit analysis. What if for step, let's see, say step 3, I did it wrong. Now you know it's going to be wrong. I see this on the test all the time. Well, let's look at the wrong one. How can you tell it's wrong? Well, let's just look at the units. And moles of H2 times, oh, look at this, moles of H2 divided by grams of H2. Is this the unit you want your final answer to be? No, it's wrong. And therefore, since nothing cancels out, this tells you it's wrong. Oops. So once again, unit analysis, looking at your units, what cancels out, because up here where it's correct, you get the correct units. That's what's left over. So that's an important thing. Now, I wanted to do overkill today, and trust me, I did overkill because students mess up that problem on test 2. Ooh, I gave away a secret. Yeah, it's going to be on test 2. But why am I spending this time? Why is that important? Or better yet, what is the reason? Well, let's talk about that. You're lucky because your instructor, me, has many, I hate to say this, decades experience working in chemical plants. In the companies I worked at, part of my job was to write the procedures, the step-by-step thing they should do in a chemical plant to make molecules. Molecules, those you also know as the products you use. Example would be the key molecule in fabric softeners. I worked for a company that did this. Another company, the key molecules that are used in hair conditioners and soaps. I worked for a company like that. And also I worked for another totally different company that made the key molecules that held sand together to make molds to be used in foundries to make things like your car engine or manhole covers. Next time you see a manhole cover, take a look at that. That solid piece of metal is made in a foundry, and they have to have a mold, and they pour the metal into the mold. The metal solidifies, the sand, and what holds the sand together is called the resin, which is a fancy name for glue. Comes apart after it's been heated and the metal sets, and you pull out your manhole cover. Or same thing with a car engine. One of my more pleasant memories at one company, I developed a brand new resin that was environmentally friendly and also stronger, which are both good things. And it was used heavily by the Ford Windsor plant in Windsor, Canada, right across from Detroit. And after they started using this new resin that I created, my last patent, I got a call from the VP of Marketing and Sales, who said the superintendent of this huge foundry for Ford in Windsor wanted to meet me and thank me and some of his people. So I took a trip down there, got a beautiful, it was amazing tour of the whole foundry. That foundry site was bigger than COD. It was huge. And that day they're making V8 engines for, I forgot what Ford. And I got a tour, and afterward they thanked me because one, they had less problems because it was a stronger resin, held the sand together better. And two, all their neighbors started thanking them because it didn't stink as much. Because when you put the metal in there, part of the process is it burns away a lot of the resin, glue, and that just goes up into the air and stinks up around foundries. It doesn't smell that good, but this lowered their emissions greatly. All right. But why do this sort of thing? Well, let's take a look. Say you want to react A and B to make C, like a fabric softener, and you want to make a lot of C, like about 40,000 pounds. How do you know how much A and B to react to make C? Well, you do the same 3-step process that I've just showed you. And other companies will do a reaction where I think the highest one I've ever done is 160,000 pounds they're making. And that means you started with a little more than 160,000 pounds of starting material, and at $1 a pound, that's a lot of money you're dealing with. And I had the right procedures. And when you write a procedure, you don't want to mess up, because if you do, now they've got a lot of waste chemical. You've blown $160,000, another 10, 20,000 labor, and then they got to get rid of that stuff. So that's more money. It probably adds up to $200,000. What I always did personally was I would do those calculations very carefully, on one day, far in advance where they needed the procedure. And then about 2 or 3 days later, I'd start fresh and do them again. Then I'd calculate them, I'd have them written down, I'd check, are they the same? If they weren't, I better go back and find out where there was an error I made, because I don't want to make an error in a chemical plant. Because if you do, also people can die. Because if you mess up real bad, and it happened out at a company I worked at, but the competitors, they've made a horrible mistake, stupid, horrible, and it killed 3 people. So you always have to be very careful. But I never made had a problem where they weren't the same. Now, do I have some time? I do. Let's teach you a little thing about chemical plants. Now, when you talk about chemistry and chemical plants, think about if you're making scrambled eggs for yourself and maybe another person for breakfast. A couple of eggs, you cook it on your stove. What if you're cooking for 10,000 people and you have to serve them all at the same time? Now it's a whole different ball game. And chemistry is the same thing. You can make a small amount, but when you go to a chemical plant, it's a large amount. And what are we talking about? Thumbs up, people. Do you see that silver tank wagon on your screen right now? Truck with something behind it? Thank you. This is called a tank wagon. You've probably seen them in gasoline stations. They are standardized. They're 5,000 gallons, 40,000 pounds, period. If you notice the ladder there, one company I was in charge not only of research, but QC, quality control. And when one of my chemists was sick, it was dead of winter in a snowstorm. I had to climb up there and look inside the tank wagon to make sure it was clean. Not one of my fonder memories in life, but I still remember it. Now, the reactions I've done procedures for, we're talking about 4 of these. Think about that. That's about 160,000 pounds or 40, let's see, 5 times 4, 20,000 gallons. That's a lot of chemical. And it was always exciting going in a chemical plant. And can you keep a secret? Later in the semester, I'm going to be taking you electronically to a chemical plant. I won't tell you how, but I will, via Zoom. And most people, except people who are industrial chemists, have never seen the inside of a chemical plant. In fact, that reminds me, after I got my PhD, I got mine at Michigan State, and I started working for, I'd been working a long time for chemical companies. And by then I started consulting. I had to go to Lansing, which is next to East Lansing, where Michigan State is, to help someone consult and give a talk to the DNR, Department of Natural Resources, to help them get a license, which I did. Turned out one of the people in the DNR was a former student of mine. But anyways, afterward, I went back to Michigan State's chemistry department, said hello to my old professor and his research group he had then. And they all asked me, what's it like in the chemical industry? Because the academic chemists, most of your instructors at COD have never been in a chemical plant, don't understand the whole world of making stuff and scaling it up. It's called process development chemistry or chemist, and I am one. And with that, oh no, we've run out of time. With that, don't forget, the amnesty program ends tomorrow. I don't know, whatever. I'll give you till midnight tomorrow to get any past labs. If you don't have them, email me and I'll send you a copy. Also, if the link is closed, email me your past labs. And on Friday, we'll go through balanced chemical equations. I think we're going to start chapter 6. We're really going good. With that, gang gesund. Bye.